What's up, YouTube? I'm back again with another topic review for the Data Science Flex program at the Flatiron School. If you're new to this channel, or this series in particular, I am a student at the coding bootcamp called Flatiron School in their data science program currently. I'm in phase 3 of 5. There's about 10 modules per phase, so as a new kind of study practice, for phase 3, I'm vlogging about each module as I finish it and kind of reviewing and sharing my understanding of the content covered. So, before we get going forward, my disclaimer, always throw, I'm not doing this on behalf or for Flatiron. I don't necessarily know that some of the people at Flatiron know I do this, but Flatiron as an organization is not aware of, me blogging on their behalf or anything like that. So I use some of their examples and a little bit of their content cherry picked from the curriculum, and some graphics and things like that. So most everything that you find in the notebook, if you follow the GitHub link down below, is going to be stuff from the Flatiron curriculum, or maybe my wording of stuff from the Flatiron curriculum. So with that out of the way, today we're reviewing Module 24, which is all about regularization, which is really just a fancy way, or it's a particular way of optimizing your machine learning model. Before I get going with that, I wanted to mention this is my first video I'm recording as a 26-year-old. I just had a birthday a couple days ago. And one of the things I did for my birthday was I upgraded my desk setup here a little bit. So I'm going to show you guys that right now real quick. So let me turn my background blur off also. Yeah. So I've had this shelf here all the time, but I had a mini fridge that was here that I wasn't using anymore. And this bookshelf you see was over here. Right now I've got a whole lot of nice empty wall, which I've actually been using for handstand push-ups and that sort of thing. But my computer used to be computerception down here on my desk, which was kind of cool. But you'll also notice I have a Surface Book too, so I have this kind of flipped backwards, so the screen's a little bit more towards me. So it was down here, and that takes up a lot of space from my desk, right? Even though I like having the wireless keyboard and mouse, it's super nifty. But anyway, so I moved the mini fridge out of the way, just completely out of here, not using it anymore. Moved my bookshelf over here, and so I was able to slide my desk this way, so that the shelf, instead of being on the left side of the desk, is in the center now. So now I can just sit here right in the center of my desk, and my computer is at pretty much eye level. And that's supposed to help with productivity and stuff, having your head sort of tilted straight ahead or slightly upward, as opposed to tilted downward tends to make you a little bit drowsy. So it's a little messy right now because I got my mic and everything out here. I really need to come up with a better solution for my microphone. But it's nice. I like it. Everything's got there's no clutter. There's no loose papers or pens or anything laying around. There's 6 different things that I can pick up, dust it, and go. I did a little bit of cable management down here as well. That power source from my computer kept kicking it all the time, so I velcroed it to the wall, as well as the power strip. You can see I rest my feet on the wall back there quite a bit. But yeah, so first episode with this new desk setup, and also first episode, as a 26-year-old. So that's exciting. There we go. Cool. And now the camera is on a little bit of more of the same plane or level. Try to get it framed correctly. There we go. As the computer screen. So I just kind of have to glance back and forth to talk to you guys versus looking at my computer. So yeah. So with that all out of the way, now we can get into the curriculum and the interesting fun stuff. So as usual, I got my one pager that you can't read because of the background blur, but we've got mean squared error, residual sum of squares, object-oriented programming, a lot of things from a lot of different modules that come back up in this module this week. And as you can see, fairly short list, longer list than last time though. I'm really struggling to get this on the frame. Maybe I'll just make that the JPEG. I don't know. But the back of it's like all filled up, right? So if you watched it before, you know the drill. We're gonna move now over to the Jupyter notebook. Okay. So we're talking Module-24 topic review today. There's two kind of broad topics that this module covered, which was kind of weird. Is this particular module seemed like they were just kind of throwing in a few like extra things like at the end of like a larger point being made, so there was like practical skills that I gathered like under this model optimization stuff, and then they kind of seemingly like somewhat randomly kind of just threw out this like stuff, which this is like just kind of standard practices in the industry and like the data science industry and understanding that sort of stuff. So that got me thinking that I might start doing, instead of topic reviews for each individual module over like everything in the module, maybe zeroing in on like one or two like more interesting things from that module in the future. I don't know, but today we're just gonna keep going forward as we have been and just do our best to talk about everything that was covered in the module. So first, I'll talk a little bit about these model optimization methods and techniques, and then we'll wrap things up with talking a little bit about data science processes. So we've got our kernel up and running. We're going to import all of our packages. Not a lot of code this episode either. A lot of the stuff covered today is like, the way to code it isn't really different than anything else that I've covered before. So it seemed to make more sense to more like cover like the conceptual side of things. So yeah. So real quick, straight out the gate, we're just going to talk about a few cool things available to generate data. Why would you want to generate data, right? As opposed to like actually gathering like real world data, like actual observations from the real world, to kind of prototype different data science pipelines, for example, or just see how different algorithms behave with different types of data that might give you, better, stronger intuition on what type of algorithm to use to the real data that you're using. There's all sorts of things to make simulated data for. So these are just like a few scikit-learn tools that make that available to you. So if you go to the GitHub and you look at the link on this index, the APIC and BIC file, these all are hyperlinked to the docs for these particular functions from scikit-learn. And these all come from the scikit-learn datasets module. So you're going to, from sklearn.datasets, import whichever one of these you're wanting to use. And they're all pretty self-explanatory. So this creates clusters or like blobs of data. You can make circles, moon shapes. You can make a regression line like of data points. And there's all sorts of parameters and whatnot that you can manipulate. So let's go like here and let's look at our parameter suggestions. So we have like our number of samples, shuffle. So if you have like multiple samples and you can like shuffle them, how much noise you want to have in your data. So that's going to affect like your error term, obviously. The random state, so that's if you want to like reproduce the exact same data points, you can set a random state. Returns an x and a y, which your y is going to be, it says array of in samples, and then your x, it says array of in samples 2. So now that I'm reading that, that's actually the first time I've read this particular portion of the docs. Your y is going to be like a vector, right? Because it's going to be like a data series, a single column, right? And x could be a single or multiple features, which is why it's capitalized and why L is not. So anyway, we're just using the make moons function here, but these all work the same. They all have pretty much the same parameters that you can pass in. We're declaring our data frame, providing a little color dictionary for the matplotlib to color code everything right down here. And so we have 3 different clusters, if you will, or groups of this data. So, or actually, I think in this example, there's only going to be 2. But you'll see. So we're going to iterate through each of those groups, and we're all going to plot them on the same axes. Yep. So, yeah, that's my bad. Not that it made a difference, but it was bothering me. So you can see we have these like moon shapes of like data points, and you can figure how like that would you could like just like a simple like purpose, or you could just practice fitting a line to this data, or classifying the data, because there's clearly like 2 different groups. All sorts of purposes for it. So this next, get away from me. This next cell is an example of how you would use this for performing a linear regression. So this is showing you how different amounts of noise, remember I like mentioned earlier that would affect your error term, how that's affecting your regression line, your best fit regression line, that is. So that's just one example of how you could see how different data distributions will affect your actual like model predictions without having to actually gather real world data. So yeah, that's pretty much that for data generation. Not a whole lot of like just riveting stuff here. Just like the fact that these functions exist is kind of the big point, which is pretty cool. They're pretty nifty little functions that you can play with. So what most of this module was really like about, or the big thing to really take away from it, was penalized estimation and everything regarding it. One of these days I'm going to figure out how to make that not happen. So penalized estimation basically is when you're estimating your feature or parameter coefficients. You're penalizing the model for over complexity or overfitting. What the point of penalized estimation is to prevent overfitting from occurring. So there's a couple different ways you can do that, at least that we talked about in this module. They are a ridge regression and a lasso regression. And all the calculus is here. We're not going to go much into how to like really into like how to code these models together, because the syntax for the code and everything itself, and like the pre-processing for the data, all that sort of stuff is pretty one for one with like a linear regression. You're just calling like a different function. You're just making a different function call. You're calling, ridge regression or lasso instead of linear regression. But the calculus is here, and so you'll notice some like similarities, right? So this is our cost function, so that's our observed data point minus our predicted data point, and we're taking the square of that, and that is equal to this, which is like reminiscent of the y equals mx plus b, but now our y is on the other side of like the equatorial symbol here. We've seen this before where y hat is represented as mx of I plus b. And then we're squaring that same as here. So that's our like normal cost function for just like a simple linear regression. For ridge regression, which is also referred to as L2 norm regularization, whatever that means. But if you ever see that, it's talking about a ridge regression. Is similar, so we're still taking the square of the difference of our observed and our predicted data points, right? But we're incorporating this penalty term into things, the lambda expression here. And the specific calculus on this changes a bit when you include multiple predictors. so you're basically, for ridge regression, you're going to have, like, let me see if I can highlight this correctly. Whoops. I can't click on it because then you're going to not be able to read it. So everything you see from this sigma to the other side of this sigma here, if you have multiple predictors, you're only going to have this one sigma. That's all going to be enclosed in parentheses basically, and you're going to add it up for each parameter that you have, to the nth degree basically. Similar to the addition rule with derivatives. So lasso regression is similar to ridge regression, but it's different in the fact that lasso regression so ridge regression, the reason it's penalized estimation is because it reduces some of the parameter coefficients based on like how many parameters there are, and like if you have any like parameters that are particularly large or something. So there's a lot being packed into that little like lambda symbol right there, right? The difference being that you take the absolute value of your penalty term times m, your parameter, with your lasso regression. And what that does is it makes it so that instead of just reducing some or all coefficients, parameter coefficients, you're doing that, but maybe you're also bringing some of them to like entirely to zero. So you can see here, like, if x equals 0, then m times x equals m times 0, which is all equals 0. So which that effectively eliminates some features, right? If you bring the coefficient to 0, then whatever the parameter is that you're multiplying it by, it's going to come out as 0. So that's the big difference. Is they're both ways of penalized estimation. They both include the penalty term lambda, but lasso regression also has the embedded feature or function of it that I don't want to like use the words feature and function like out of context here too much. Lost my train of thought. Lasso regression also eliminates some features because it makes some features equivalent to 0, which is the same as eliminating them entirely. So that's your big difference between lasso and ridge regression. They both penalize the model for like over complexity and overfitting and that sort of thing. These are both available in scikit-learn and the linear underscore model module. You call them just like you would like a linear regression or any other kind of like model object in scikit-learn. So this is one of those things that just seemed like it kind of like got randomly like thrown in there into the curriculum, but it was interesting nonetheless. So there's this thing called AIC and BIC, which came after. It stands for APIC, I think is how you pronounce this name. APIC's information criterion, and BIC is the Bayesian information criterion. So APIC's information criterion came out, big success, and the Bayesian statisticians were like, no, we want to have our own. And they came up with the Bayesian information criterion. And the basic difference there, what makes the BIC Bayesian, is the fact that it incorporates historical probabilities into calculating like the future ones. So this is the calculus for it. This ln, if you don't know, means natural log, which I probably don't have any business talking on like the mathematics of that, so Google it. But anyways, this is the formula to calculate your AIC or your BIC. K is the amount of parameters that you have, so how many features are in your spreadsheet basically, minus your target variable column. L hat is the maximum value of the likelihood function for your model. So one of the things that makes AIC and BIC so easy to use, what they would be used for, is evaluating if one model is better or worse than the other, basically. They're easy to use because they're automatically calculated. The likelihood function for the model is automatically calculated when you build the model. So it doesn't necessarily require any extra computation in order to perform this analysis, as opposed to, like, say, gradient descent or something, which or like fitting a regression line, which can get pretty computationally expensive. N is the number of observed data points, like as usual. So you can see here that they're the Bayesian one. They're just incorporating the natural log of the number of data points times the length of the parameter space. Somehow or another, that incorporates previous probabilities or historical probabilities into the calculus. Probably not important as a data scientist on your day-to-day to really understand, like, be able to, like, do by hand, like, all the math behind there. It's just important to understand, basically, that if you have two models, in whether you're looking at AIC or BIC, whichever one has a lower AIC or BIC score is going to be the better model to use. Cool. So that's penalized estimation and APIC and Bayesian's information criterion. So now we're going to look at different feature selection methods. So at this point in the curriculum, things started to sort of, let me see what time we're at. 20 minutes? Okay, not bad. Things started to kind of, all these like different things we're learning seem to start to be coming together into like a coherent framework. All right. So the first feature selection method that you have, available to you is, of course, domain knowledge. So these are just, there's kind of like earlier with the, the data generation. Not a whole lot of like riveting stuff here. It's just important to not just be good at the math and the programming, but also like understand on a qualitative level the sort of ins and outs of whatever the domain is that you're doing data science within, right? So that can be as simple as staying up to date with the most recent literature, and I would argue that that's important for not even like the unique domain of like whatever product or service you're like contributing towards in your data science work, but probably also on data science itself. There's a lot of research, like new research in data science, and we're learning new stuff literally every day. So it's probably important to stay up to date on the literature for your particular domain you're working within, but also the domain of data science itself. Because you never know when like some cool new algorithm might come out that has been exactly what you have been needing. Communication with stakeholders. So it's really important to, when you're working as a data scientist, like communicate with your stakeholders and kind of get an idea of like what are they expecting, what are the, not just like the deliverables that they want, but like what do they want to get out of like the deliverables? What's like the real like end result? What's the difference that they're wanting like you to make? And that's going to give you a good idea about kind of how to go about your data science procedures. Expert opinions, of course, because you as a, data science is inherently multidisciplinary. So as much as you might stay up to date with the domain specific literature, you're not going to be as with it as somebody who that's like the thing that they do. So talking to experts and getting just like a better lay of the land in that sense, just talking to other people that just know more than you about the specific domain you're working within. Listening to end users is one that I threw in there because it's like important to, so like an example with, I really hate to be advertised to, like I loathe being advertised to. Every time an ad pops up on YouTube, even I'd roll my eyes in the back of my head. On TikTok, they've gotten pretty nifty with it in a way that doesn't actually bother me. They're actually like forming ads in a way, people on TikTok are making ads in a way that you don't really realize that it's an ad quite at first. It's because it's not some like $100,000 commercial they put together. It's like just some TikTok, and that doesn't bug me as much. And I think that some marketer somewhere along the way started talking to like the end users, the consumers of advertising content, and being like, what do you not like and what do you like about advertisements? And they probably came to that idea. So yeah, it's just important, I think, to understand like the end users. Like if you're trying to optimize some product, what do the end users of the current iteration of the product, what do they like about it? What do they not like about it? stuff like that. And many projects, of course, like, so, role play, developer, end user, etc. What is that? Oh, so like when you're doing a project, start like a little mini project, like just for the sake of learning. You don't have to reinvent the wheel. You don't have to invent like the next like Jarvis or whatever, right? But do a project that is gonna like never be anything that somebody actually wants to like use, but you'll still learn something from it, and then you get to like think about things in the from the standpoint of a developer or a technical person in general. You could, once you've done and you've like created the thing from your project, then you can like use it as an end user and see what you like and don't like about it, and that's going to give you a lot of insight on the sort of human experience side of the domain that you're working within, I think. So there's domain knowledge, and we have wrapper methods, which this is an example. This would be like recursive feature elimination, which I used ad nauseum along with stepwise selection in my phase 2 project. Basically what wrapper methods are is they're whatever medium they come in, they're subsetting different sets of the features available, the predictor variables available in the model, and figuring out what's the best combination of those features by actually taking a subset of features, building a model, and then looking at the statistics and the scores on that model, like your R-squared value, for example, or your coefficient level, or like whatever, right? Problem is, the wrapper methods are very computationally expensive because you have to build a model for every iteration or every like subset of those features, which if you talk about like you have n features and you're dealing with n factorial like subsets of those features, you have a lot of models to build in the first place, and then you have to fit the regression line like for every single one of those models. So that gets pretty impractical pretty quick, especially when you're dealing with large amounts of features for one, and large amounts of like observations as well. So wrapper methods, time and place for everything, but the part of the problem that I realize now in my phase 2 project is I relied on wrapper methods a little bit too much, and that's part of why things took so long. You might, if you watch any of those live streams, you might remember me having cells that would run for 45, 90 seconds, 4 minutes at a time. It was totally not having a good time. So filter methods are a little more computationally efficient than wrapper methods. So basically what a filter method is you're coming up with some sort of threshold for, like, I used in my last project variance inflation factor and multicollinearity, so I just kind of arbitrarily said anything beyond this threshold, we're throwing it out. That helped a lot. That kind of reduces the amount of models that need to be made. You still need to like build and train and test like some amount of models, but you don't need to do it for like every single subset of features the way you do with wrapper methods. So in my last project, I used kind of a combination of wrappers and filters predominantly for my feature selection. The embedded methods are methods where the feature is selected or eliminated through some aspect that's intrinsic to the model itself, or the algorithm that builds the model itself, right? So a great example of embedded feature selection is lasso and ridge algorithms. Maybe ridge not so much because that's really just penalized estimation, but lasso for sure, because like I said earlier, with lasso, some of the feature coefficients might be reduced completely to zero, which mathematically eliminates those features. So that's not based on variance inflation factor or subsetting features and looking at R-squared or like any of that. It's just intrinsic to the algorithm itself that the model is built with. So that's probably, I don't know for sure because I'm not a computer scientist, I'm a data scientist. That might be the most computationally like cost-effective method, because it's like you build a model and you're getting your feature selection all at the same time. That said, there's time and place for everything. So all of these things you should really, that's kind of where data science becomes art or whatever, is like having an intuition for what's like the best balance between all four of these things that you have available here for your feature selection. So that is it for model optimization topics. Now we're going to talk about data science processes. I'm going to write a letter to Microsoft and tell them VS Code notebooks are being dumb. So anyway, there are several methodologies that have been standardized by the data science community to help us guide a sensible and efficient workflow for data science projects. It's important to note that these are really guidelines and they're not strict rules, and it's pretty common to kind of step in and out or backwards and forwards or whichever phase. So my sense that I got when I was kind of reading through the curriculum was that what's really important isn't making sure that you go from one phase to the next directly in like a linear fashion, but what's really important is just taking a moment to consider like and recognize like what phase are you in, right? And that's going to help you, better communicate to other people involved in the project, like what you're doing, what your like purposes and goals are for what you're doing, what like they could do to help other people that you're bringing into the project. It's just important to be aware of like, what am I doing right now? And like, why am I doing it? What am I trying to get out of it? Right. So these are just a few kind of standardized protocols, that are common within the data science community. So this first one is CRISP-DM, which stands for Cross-Industry Standard Process for Data Mining. Data mining is a pretty old term. You don't hear that a whole lot anymore. But what that specifically refers to is the portion of data science where you're trying to, the actual modeling portion where you're trying to detect like patterns and find like predictive relationships and that sort of thing. So you can see we begin with our business understanding here. That goes back to our domain knowledge and communicating with stakeholders and that sort of thing. Data understanding, you got to like know like where you're getting the data from, like how is it encoded, like what are all these like different, how many features do we have that are categorical, how many of them are within the categorical variables, which ones are nominal, which ones are ordinal, like stuff like that. So once you understand the data and the business that you are using the data in respect to, then you prepare your data. So this is where you're like dealing with missing values, maybe engineering new features. Yeah, everything that you pretty much, but 90% of what you saw on the Phase 2 project live streams. Encoding data. So like I had like a column that was a bunch of dates and it was just like in strings, and I wanted it to be like encoded in a way that I could actually like do calculations with it. So I encoded it as converted that column to like date time objects, stuff like that. Modeling is, that you're building your model, you're fitting your regression line, you're going back and selecting features, optimizing it, building your model again. And so you can argue that feature selection is part of like your data preparation. So you gotta go back and forth here. They got a couple arrows here on purpose. You go back and forth here pretty frequently, and then once you get a model that you're happy with, then you evaluate it, and that's where you're actually like, as a data scientist, you're taking like all the numbers that got spit out and communicating them in a way that non-technical people can understand and make decisions and take actions with. Deployment is, of course, the phase where you're actually taking actions and implementing like what you've learned into the product or service that you're working on. I don't know a whole much about the deployment phase of things because I'm still a student and haven't actually worked as a data scientist yet, so I'm very excited to learn about that one day. This is the one that I thought that kind of, I don't know, like resonated with me the most. Knowledge discovery in databases. So first you have to select, like, you have all this data available. Which data are you going to use, right? Pre-processing is, again, dealing with missing values, encoding your data, train test splitting, like, like sampling for which data is your train data, which data is your test data, all that sort of stuff. Transforming your data, which is a lot of math stuff and basically makes it a little bit, your model's a little bit better at detecting patterns, which is the next phase. Data mining, we're actually detecting what patterns and relationships exist in the data, what things predict other things, that sort of stuff. And then again, your interpretation and evaluation phase is basically you taking your technical knowledge and using that along with the outputs of your model to communicate worthy suggestions to your stakeholders. Let's get all this out of the way. And then OSIM, which as much as KDD, like, I like it a little bit more. I have no idea why, just like completely hunch thing. OSIM seems to be the most sort of like comprehensive one. These all kind of like cover the same like things roughly. So you obtain your data, of course, you scrub it. That's pre-processing your data. Exploring your data. So that's something that the OSIM kind of incorporates that the others don't. I think it is like nice to like, just kind of like explore your data, like check out like, do your like data frame dot describe and look at, is there anything with like really outrageous like standard deviations or means or, just whatever kind of like fun stuff. So of course, you build your models and you interpret your models, right, rather than like evaluate. Same thing, right? You're looking at what the output of your model is, and you're using your technical knowledge combined with your communication skills to inform non-technical people about what suggestions are being made by the data. And that, ladies and gentlemen, is topic 24 of the Flatiron Data Science Bootcamp, or at least it's what I got out of topic 24 of the Flatiron Data Science Bootcamp. So, I hope you got something out of this. I hope, again, I've said this at least, I think in most videos at least, calling this a boot camp is really kind of an understatement. We're learning a lot more here than just how to code. There was hardly any code in like this video today. For example, it's important to know how to code, but it's like kind of like there's no point in knowing how to turn a wrench if you don't like understand the machine that you're going to turn the wrench on, right? So Flatiron, I have been really impressed with so far, has done a great job of providing that kind of understanding of what you're coding about as well, rather than just like here's the syntax of how to like write your code. So if you're on the fence about coding bootcamp and you're seriously considering data science, I would recommend seriously considering Flatiron, because as you can see here, we're learning a lot of really cool stuff. Or if you're just generally interested in data science, period, I would look into Flatiron. So yeah, that's it for today. I will be back soon with another topic review for Module 25. We're going over classification algorithms and stuff like that, which is going to be really cool because we're getting into using like regression lines that are not necessarily linear and stuff like that. So that's going to be really cool. Hope you enjoyed the video. Hope you got something out of it. Highly recommend Flatiron. Check out the description below for any relevant like links and that sort of cool stuff. And I'll see you guys next time. Peace.